So what I would like to continue with is a presentation on time domain analysis of MEG and EEG data with event-related fields and event-related potentials. We have already partially looked at this yesterday, and actually computing an ERP, I never consider that like to be worthy of let me think one step forward like this. The camera is totally pointing in the wrong direction, so as such. Let's see whether it's going to track me. No. Okay, so no. So normally I don't give like 3/4 of an hour presentation on how to compute an ERP, because computing an ERP is simple. But what I've been trying to do in this presentation is to also link it a little bit to the other things that we're discussing in these days. And what I would like to start with is this notion that MEG and EEG are the superposition of many different sources. So here I'm showing an example with EEG. And if we have a source at the back of the head with a relatively low frequency signal component, and if we have a source at the front with a relatively high frequency component, then a channel that's in between is always going to pick up both sources. It's going to be a linear mixing. A channel at the back is also going to be a linear mixing, but it will have stronger weight of the source that is occipital, and a channel at the front will have a stronger weight of the source that is frontal. So that means that each channel, in principle, sees each of the underlying brain regions, and that's what we have to deal with during the analysis. Very shortly, it's like more about the acquisition side. So the data set that we're working with has both EEG and MEG, but most of us are working with either EEG or MEG. If we record EEG, it's often 64 channels, like 500 hertz. If we then do an experiment that lasts an hour, we have possibly like 500 megabytes for a single recording, and then we would have like 30 subjects. So that's an amount of data that easily fits on a USB stick. With EEG, there's many companies. That also means that we have many different file formats. With MEG, we have way more channels, and it's actually something that we don't really choose ourselves because they just come with the system. So with the CTF system, with the NeuroMag system, we have 306 channels. We typically record at 1,000 hertz. And that means that one hour is approximately like 4 to 8 gigabytes of data. If we then again do about 30 subjects, we have amounts of data that don't easily fit onto a USB stick anymore, but that could fit on an external hard disk. There's only a few MEG companies. That also means that we have only a few types of data formats to deal with. We have NeuroMag with FIF files that we're working with here. So at the moment, we have a CTF system. Here in Marseille, they have a BGI system. There's not so many BGI systems around anymore, not being made anymore. But soon we will also have more OPM systems. And with OPMs, the market is going to up, so it's going to open up, so we're going to have more file formats again. I think, so yesterday, Joanna already mentioned BITS, the brain imaging data structure. I think that's going to be a more and more important strategy for us to organize our MEG and EEG data for archiving within the lab, but also for sharing between labs and hopefully also for public sharing. We also record a lot of auxiliary data, and we've mentioned it a few times, like we can record EOG channels, we can record ECG channels, and we can use them in the artifacts cleaning procedure. But we also record, for example, anatomical MRIs, which is something we're going to look at tomorrow. We also record behavioral data in a lot of our experimental sessions, and that's time resolved. That is mostly encoded as triggers. But sometimes we also record the behavioral data using a more complex setup, such as a video camera. And we have eye tracker data. And then we have other data that can sometimes be really important for the experimental research question, like handedness, gender, age, but also very specific questionnaires for the research question. And all of these types of data, they can be stored and represented in a standard way in bits. And I must say that the auxiliary data is usually quite small, but it's very diverse. And this diversity makes it a little bit harder to organize it in a clean fashion. So BITS is there to organize all of your data. It's a way to organize existing raw data. There are some efforts in also using BITS for derivative data, but that's not yet standardized. The BITS for raw data is standardized. And with BITS, we're not storing the data in a new file format per se. We're using existing file formats. And BITS is also not a search engine or not a data sharing platform, but it is being used by search engines and data sharing platforms such as OpenAI. And a lot of you might have heard about FAIR, findable, accessible, interoperable, and reusable. And BITS mainly focuses on the interoperability and the reusability. And if a data set is reusable by someone else, it's also going to be more reusable by yourself in the future. So actually investing yourself in organizing the data in a clean fashion is going to be beneficial for the research that you're going to do in half a year from now or a year from now. So that's just like an important consideration. So if we have acquired our data and if we have organized in a clear fashion, we start with pre-processing. So prior to pre-processing, we do some data curation. We figure out which subjects fulfill the criteria and which data we want to keep. And we collect all the files, we name them consistently, we bitsify it, and then we do the first processing steps. And these first processing steps are not so much dependent on the research question. There's the quality control, artifact removal, filtering, baseline correction, etc. There's also the pre-processing of anatomical MRIs. And it's the later steps in the analysis that are usually tightly linked to the research question. And it's always a little bit difficult to say, like, where does pre-processing end and where does the processing start? Or where does the analysis start? Like, what's the difference between processing and analysis? And usually it's a gradual distinction, but at a certain point, the research question becomes more important. What I'm going to focus on is on the averaging of event-related potentials. And I'm going to link this a little bit to statistics. So tomorrow we're going to deal with statistics in a much more elaborate fashion. So I'll very shortly touch upon it, but I think it's a relevant thing in relation to event-related potentials that I want to highlight. So if we take a simple event-related task, then we know that the signal-to-noise ratio is not high enough to observe individual brain responses on the individual events that we're presenting. And therefore, we are repeating the same stimulus or the same task many times. And that's what we call trials or epochs or segments. Like we call it differently in the different toolboxes. But it's a repetition of the experiment within one participant. For example, we might have one trial every 5 seconds, and that's going to give us 600 trials in 1 hour. And this experimental manipulation that we care about is usually a subtle difference between trials. Then we record EEG and MEG, and usually the signal of interest is only 1 second around the stimulus. So that means that after the participants being recorded for about an hour, we have about 600 seconds of usable data left. And that's actually what goes into the analysis. That's interesting because also if we consider like resting states, EEG or MEG, it's often the same order of magnitude of data that we're acquiring for a single individual participant. That would be like 10 minutes, which is also 600 seconds. If we then look at the analysis of a single event-related task, so we have 600 trials, and then in this data set, so this is for the Wakeman and Hansen data set, so we had about slightly over 600 trials where a phase was presented, either phase or a scrambled phase. We can split these into different conditions. So we have 200 unfamiliar faces presented, 200 familiar faces like celebrities, and then we had 200 scrambled faces. But actually we had 300 in each. So we had 300 familiar faces and 200 familiar faces, 200 scrambled unfamiliar faces. And each of them is presented twice. So there's 100 familiar faces presented for the first time, and they're also presented the second time, and et cetera for the other. And that means that there's a multifactorial parametric design in this experiment. So we have we have the factor of the type of stimulus, and we have the factor of whether it's the first or the second presentation. Okay, so if we're just starting off with a very simple analysis, we could just say, let's pool all of them together. Let's just compute the average of all those 600 trials, and let's see whether we have a visually evoked potential. And that would actually be a very good strategy to just evaluate the quality of the data, and also to help you to make choices during your pre-processing. Because subject was sitting there looking at the screen, there should be a visually evoked potential. That's not a scientific question, that's just a given. So optimizing the quality of your visually evoked potential is one way that can guide you in making decisions in your pre-processing pipeline. Of course, where it gets more interesting is if we start looking more into the scientific question, like, is there a difference in processing phases versus scrambled phases, and then we would group them. We would basically take these ones, and these ones we would look at this contrast. We can also look at the difference between unfamiliar versus familiar phases, like ignoring the scrambled ones. Or we can look at even more subtle differences, like the first versus the second presentation of a phase. But you can, of course, also ask the question, like even going into more details, whether there's an interaction between famous and unfamiliar phases and the sequence of presentation, because the famous phases the participant would have seen before, whether unfamiliar phases or not. So this is like a parametric design, a factorial design that is often embedded in our experimental structure and that we often report. And this is something to keep in mind in the analysis. So this is how our data could look like. So here I'm showing the data for all the EEG channels. And what you also see is that there's these different stimuli. And what we do in the pre-processing, the other button, is that we cut segments. We define a segment around each file. So in future, these segments are called trials. You can also call them epochs. And for each epoch, we basically cut a piece of data. And what I'm going to do is I'm going to vertically shrink this a little bit so that it fits better on the slide. So if I take all of these pieces of data and if I put them like this, then each of these is a matrix that is about, like for the EEG, it's typically about 100 channels by about 1 second. So that would be like for EEG about 100 channels times 500 time points. And that's basically the data that you can see if you look in the data structures of EEG Lab and ME Python and Future and Brainstorm. Like, so this is the trial, the data of a single trial. If I now like zoom in a little bit on these trials, what we have is we have an organization that is channels by time, and then we have multiple trials, like multiple repetitions of stimulus. If we now look at a single channel is basically a row in this matrix. And so for a single channel, we have a repetition of the stimulus over multiple trials. So this is showing for a single channel, the single trial responses. So this is on the first trial, this is on the second trial, this is on the third trial. And what we do in computing ERPs is that we simply take the average. And then if you take the average of a single trial, which of course is like not really taking the average, then it looks like this. And what we do is we can gradually increase the number of trials that we include the average. And what you can see happening is that there are certain patterns are remaining, like this part is also still present here, whereas other patterns, like this part, is gradually decreasing. So there is something in the data that is consistent over trials, and there's also a lot of brain activity that is not consistent over trials. And it's the stuff that is not consistent over trials that we often refer to as noise. To be honest, I don't think it's noise per se. It could be noise, but it's also like it's other brain processes, and it's a brain process that we don't care about. As such, it's not noise, but it's the parts of the signal that we don't care about. The notion that we're using with evoked or event-related activity is that we have an event, and that following the event, or sometimes preceding the event, there is something happening in our channel of interest. And if we repeat the same event many times, and if we sum it and divide by the number of trials, that activity is going to remain the same. At the same time, we have noise, or brain activity of no interest. And the effect of the averaging is that the brain activity that is the same over all trials remains, whereas the noise gets smaller and smaller, because the noise is random over trials. And that gives us the event-related potential for EEG or the event-related field for MEG. So the brain signal is assumed to be constant over trials, the noise is independent over trials, and averaging over trials improves the signal-to-noise ratio without actually changing the amplitude of the event-related potential. Like the event-related potential is assumed to be there every trial. Averaging is not going to make that larger or smaller, but it's the noise that's getting smaller. So the signal stays the same, the noise gets smaller. And the amount with which the noise gets smaller depends on the number of trials, and it's proportional to the inverse of the square root of the number of trials. So if we have 10 trials, then the signal-to-noise ratio increases with a factor of 3. And if we have 100 trials, then it increases with factor square root of 100, which is a factor of 10. So that also explains why we need a lot of trials. Because actually to get the signal noise ratio down, we really need a large n because we're taking the square root of n. Of course, there's also other types of data, other types of signals present in the data that we're not going to recover using this strategy. By the way, as the people taking photos, I will share the slides with all of you, so you don't have to take photos per se. But there's also activity that is elicited by the events, elicited by the stimulus, where the activity is time-locked to events, but not necessarily phase-locked to the event. So sometimes it starts with an upward deflection, and sometimes it starts with a downward deflection. And to analyze this type of signals, we need time frequency analysis methods, which is going to be covered this afternoon. Okay, so if we now go back, so far I've been looking at an event potential for a single channel. But let's now go back to this idea that each channel has a superposition of the activity in different brain regions. Like that's really an important thing to keep in mind when we think about ERPs, is that the ERP shows the activity, the time-locked activity in different brain regions at the same time. So what we have is we know that so based on the biophysics, we know that there's linear mixing. So we have a linear model for ERP activity. That basically states that the data consists of signal plus noise. If we then consider two conditions, we have the signal in condition 1, the signal in condition 2, and in both conditions we have noise. The noise is not related to the task, the signal is related to the task. And if we then consider that we average the signal over many trials, what happens is that the noise gets smaller. The signal stays the same, the noise gets smaller. And that means that if we could start comparing the event-related potential in two different conditions, we're starting to compare the two signals that we have recorded. Okay, so this is easy if there's one signal, but usually there's not one signal, but there's multiple brain regions active. So in reality, this is more how it looks like. So we have a signal that is common. Actually, I think that's on the next clip. Oh, we have a signal that is related to the task. There's a visual presentation. And then we have a signal that is related to the condition. There's a visual presentation of a phase or a scrambled phase. And then there's noise, which is not related to the task. Still might come from the brain, so it's still brain signal. Again, we can compute the ERP by averaging all of the trials over one condition and now all of the trials over the other condition. And if you now consider what happens if we look at the difference between the two conditions, the signal that is common to both conditions is going to fall out. And this is an important thing that we can use in ERP analysis that are more difficult in time frequency analysis. Because in time frequency analysis, we're doing a nonlinear step in the processing. So what we're left with is that the common signal, for example, just there being visual inputs, falls out, and what we're left with is the difference between the two experimental conditions specific to those conditions. And that's usually what we look at. So here, this is not from our data that we're processing here. It's from I think it's from an oddball task where there were standards and deviants. So for a given channel, what you would get is you would get a signal in the standard condition, like in the frequent condition, and you would get a different signal in the oddball condition. But the part that we care about is the difference between these two. Like there would be a stimulus presented. We don't care about how the brain processes each stimulus. We care about how the brain processes the difference between the two stimulus types. And this is actually quite a cool paper. It's an introduction on use event-related potentials. It's worthwhile reading. And so I took this picture from it. So we start with these raw trials around each of the. So we start with the trials in the raw data for each of the stimuli that we're presenting, and then with all these trials we compute the average. And then depending on where we look, we're going to see a different pattern. So the event-related potential on an electrode here at the back of the head is going to show a different pattern of activity than the event-related potential would show for a channel here at the front of the head. And this is where ERP components come in. ERP components are features in the data that are different for the different channels, or like electrodes or MEG channels, and that are also different at different time points relative to the event. So what you can see here is that for the occipital channels, there is a difference between the two conditions that is dubbed the N2PC. So it's the second negative component, parietal occipital, I think. And whereas here at these frontal electrodes, there's lateralized readiness potential. So apparently there was a task and the subject had to press a button, and there's feedback given, which causes the subject to become aware of whether he has pressed the right button or not. So there's also an error-related negativity. So ERP components are parts of this ERP that we can link to very specific experimental contrasts in the experimental task. And here I've just listed like a whole bunch of ERP components. And I think this is a little bit like an atlas. There's just a whole bunch of them, and it's just useful to get to know all of them. The one that we mainly are looking at in this task is it's just like a visual N100, but it's also this N170, which is like a phase processing related potential. But there's a whole bunch of components, and the way that you can think of it is that a component can be compared to an ERP component can be compared to an anatomical brain atlas. But the ERP components map not only the space, but also the time and the activity in relation to a specific event. So knowing ERP components actually gives you an understanding of like the different modules that we have in the brain. And of course, there's a lot of ERP components that we still don't understand. There's whole books written about ERP components. I'm not an expert on them, but I think it's really useful to look at this. And I know that it's not, perhaps nowadays, not the most sexy methods. Like a lot of us are looking at oscillations to try to understand how the brain works, but ERP components still shed a lot of insight in how the brain processes stimuli, etc. Okay, so ERP components are identified usually on one channel, even though we report them on many channels, because then we can tell that it's specifically to one channel. And then we look over time. So as such, an ERP component is telling us when in the brain is there the activity, like it's telling us something about the latency in one condition versus another condition. Or if you look at difference waves, you can look at when is the activity different between the conditions. And what we're doing with an ERP component is we're mainly capitalizing on the temporal aspect. We're capitalizing on the role of the matrix. What you also can do is you can also look at along the other dimensions. So you can look at one time point and then look over all the channels. And still you would do that. That's something that we have on each individual trial, we would average. So that gives us information. What is the spatial distribution in one condition at a latency? Or if you compute an ERP difference wave, you can look at what is the spatial distribution of the difference at that latency. And that's where it gets interesting, because the spatial distribution of the difference means that we are zooming in on one specific brain component rather than having all brain components at the same time. So ERP difference waves are really important. So interpreting the spatial distribution informs us about the location of the activity. If we look at the spatial distribution of the difference wave, it informs us about the location of the activity difference. And if you now recall that we have this common contribution that is present in each of the trials, then we have something that is specific to the phases versus the scrambled phases. Then you can start thinking about, okay, so looking at ERP difference waves, the topography allows you to localize the area in the brain responsible for facial processing, or that is like selectively sensitive to spatial processing. That's probably, it's not one region, but there's like multiple regions, but allows you to zoom in on a specific thing without having to look at all of the activity at the same time. So that's basically what I said. So it gives you insight in where in the brain are the differences in activity and where in the brain are the components of this brain activity. So where a component is not an ITA component, but a component is an identifiable peak in the ERP or in the ERP difference that is specific to a contrast between conditions. So to summarize, EEG and MEG are the overlap of many sources. sorry, EEG and MEG are the overlap of many sources. And if we average the event-related potential or the event-related field, then we also have the overlap of many sources, but only those sources that are time-locked, and we will have them with less noise, because the averaging reduces the noise. ERP or ERF difference waves, they reveal the components that are event-specific at a specific latency range and at a specific channel, so that means with a specific topography. And by doing our experimental designs in a factorial way, that allows us to capitalize on differences between conditions or in interactions between the different factors that we have. And the uninteresting main effects that we're often not interested in, they're still useful because we can use them for quality assurance, we can use them for optimizing our pipeline without double dipping. But like double dipping is if you already look at your contrast and then see how you can maximize your contrast. So you actually repeatedly test the same contrast. Whereas the main contrast, or the main effects, you're not really interested in, you're not going to do statistics on them, which means that you can compute statistical scores for them and optimize them so that you can make the right decisions in your analysis pipeline. That's what I had to share with you on the ERPs. Relatively short, but I hope it's clear. Are there any questions?
Thank you for your talk. I was wondering, so if we if we imagine each brain responses, would they be the same size in terms of amplitude as the ERP, although they are embedded into noise and with different latency, or would it be smaller or higher amplitude?
That's a very interesting question. So the assumption that we're making in the computation of ERPs is that the response is identical over trials. At least the thing that we're going to get out is that part which is identical over trials. But of course, over trials, our participant is not always going to respond exactly the same way in each of the trials. So over trials, there is going to be variance that is going to be related to the brain activity. So if you look at the variance, so if you plot the event-related potential, and if you plot the variance of the standard deviation over trials, you might actually see that the standard deviation is larger at the peak of the ERP components than it is in the baseline. If that is the case, then there's a clear indication that that there's variance over trials. And of course, then you can also start asking the question, what does this variance over trials mean? And that's where you need single trial analysis strategies, such as decoding strategies, where you can relate the activity in each single trial to, for example, some behavioral metric that you have, like response time or visual perception thresholds, like a visual perception that changes over time, over trials. I shortly mentioned that we also have this activity which is not time locked. And one of the things that I'm pretty sure that we're going to see this afternoon is that if we do time frequency analysis or wavelet analysis on epoch data, the event-related responses, so the ERPs, are also going to show up in the wavelets decomposition. And a question that a lot of people often have is like, how can I get rid of my event-related response so that I can look at only the oscillatory activity? And one of the strategies that sometimes is used is by first computing the ERP and then subtracting the ERP from all of your trials. If you then consider what you were just asking, so that actually the ERP is the same over trials, but just varies in amplitude, then you also can see that by subtracting the ERP from each individual trial, you're not totally removing the ERP. So that means that by subtracting the ERP from individual trials prior to time frequency analysis, you're reducing the effect of the ERP, but you're not totally removing it. Which is also why I typically don't bother with it. Because if it's still in there, I just have to explain it.
Coming back to this AI new way of analyzing data, do you think, what do you think we could learn from feeding the AI with like stimulus and signal, and eventually this would find the evoked activity? What do you think we could learn from this type of analysis as compared to ERP or ERF analysis?
I think that complementary. So I think AI will be able to reveal patterns in the data that, with the simplified models that we're assuming with ERP, that we are simply not able to explain because the model is too simple. But I would also say also with AI, we still want to interpret the data in a very general fashion. So we're still making a model of how the brain works. And all models are wrong, but some models are useful. So a very simple model can be very wrong, but can also be very useful. A very complex model might be less wrong, but might also be less useful because of its complexity. And that is also why I still value techniques that were introduced already a long time ago, such as dipole fitting, event-driven potentials, because they're based on what we now consider as relatively simple models. When they were introduced, they were not simple, but now we consider them as relatively simple, because they actually also allow us to base the more complex models. So these can act as a starting point for us to think on the more refined models on how the brain responds to certain events. So I think they're not mutually exclusive.
Thank you.
Can I ask a small question? It's maybe a bit naive, but let's say you have a subject watching videos. So you have a visual activation, but not well locked in time. So you cannot recognize just a movie clip, let's say. How would you analyze it in order to understand where and when is the activity coming from? So yes.
Yeah. So this is really a relevant question. Like how do we analyze more naturalistic situations? Like what we often do is we show the same stimulus, and then subject is basically sitting in a dark environment, looking at the screen fixation course, nothing happening, stimulus flashes, nothing happening, stimulus flashes. So in that case, we know that we can, and then the stimuli are relatively far spaced, like a few seconds apart. In that case, we know that the brain has already processed the previous stimulus when the next one comes on. So that's why the ERP rationale works. If you have a constant stream of images, which is a video, of course, the brain is constantly responding to these. And what you can think of is that you have the stimulus and you have the response. If you have many stimuli after each other, you can basically add all of these responses to all of these stimuli. So you could say each of the frames of the video or each of the scenes in the video is going to elicit a brain response. So rather than having one stimulus, one longer response, you can think of it in a convolutive model. Basically, you get the temporal summation of all of these responses. That also means that thinking of this more in terms of a GLM analysis that we use with fMRI data, in a way makes more sense. And that's also what the Unfold toolbox, which is like yesterday in the bouquet sessions was presented. The Unfold toolbox is about this temporal deconvolution if you have stimuli that are very close to each other. So that is something like with ERPs, we assume that they're sufficiently far spaced that the trials are independent of each other. But if your events are close by, then they start depending on each other, and then you have to use deconvolutive strategies. Yeah. Good. There's a question there in the back.
I have a question about optimizing my effort in terms of the number of trials I have in an experiment and the number of participants. So you've shown us how the signal to noise ratio improves with more trials, but you get diminishing returns because of that square root term. Is it, if I'm trying to estimate if you like, a population value and I'm using individual subjects, is it a truism to say that the same square root of n applies to participants, or does it show diminishing returns faster or slower, assuming you're testing, as it were, undergraduates who are a pretty homogeneous group?
It's a very interesting question, and a paper comes directly to mind, but I forgot who the authors were. That was a British group, I think like 2 years ago, that actually specifically look at this, like what's the effect of the number of trials versus the number of subjects. over trials within one participant, and assuming that the participant has a constant behavior over the course of the experiment, you have the within subject participant. Between the participants, you have another type of variance. So your individual students that are participating in your experiment, they will still have different cortical folding. Which means that even if the cortical response is exactly the same, the way that it's going to show up in your EEG is still going to be different. So the between subject variance is not the same as the within subject variance. At a certain moment, you have this trade-off between the within subject variance and the between subject variance. So getting more and more trials from your individual participants at a certain point is not going to benefit the statistical power in your design, because at a certain moment that's going to be limited by the variance between subjects. But if you have very few trials per participant, then that is going to be the limiting factor. So you basically have two limiting factors. And what this paper does, and I will look it up for you, and I will give it to you over the coffee break, actually I'll put it on the forum so that everyone has it. What this paper does, it looks at this trade-off between the within subject and the between subject variance, also incorporating the cost that you have in getting additional participants. Because getting extra trials within one participant is usually cheap. Putting on a cap takes you half an hour or so, like, or instructing the participant, inviting the participant, like finding the participant usually takes even more time. So getting one participant might be a few hours of work. Getting a few more trials, that's cheap. Only takes like 15 minutes. So that's where the trade-off often comes in. To be honest, like at the donors, we often have the strategy that we're going to try to exhaust each of our participants that comes in the lab. So we're just designing our experiments to be at this level that the participant will get towards the end of the experiment still do the task properly. Of course, at a certain point, performance is going to drop down, or participants are going to gossip among each other that it's really a boring task that we should not participate. So that's also not good. But we usually try to get as many trials as we can, which for some participant groups, for infants, is not a lot. If we're recording EEG from babies, we're happy if we have 5 minutes of data. And that still takes like 3 hours, basically set up that whole experiment. So then we know that we need a lot more participants than if we're doing the same type of experiment with adult participants, where we can easily get like an hour of data from each participant. But I'll share the paper. It's a very insightful paper. It's not only on EEG. It also shows this for MEG and also shows this for fMRI. It's a very relevant thing to think about in terms of planning your experiment and doing the power analysis.
Thank you very much, Robert. Thank you.